All right, and we're back from our break. So this is the second part of our linear regression, simple linear regression in matrix format lecture. Really, the second part could be given its own lecture, but just have it as one part and part of the slides. So I will just keep it like that. So this is the second part of simple linear regression in matrix format. As part of that previous lecture, this simple linear regression in matrix format part one, we introduced matrix calculus, the idea that we're taking gradients, taking Hessians, these kind of things. What happens when we're working with matrices? In this part of the lecture, this part two, we're going to be doing probability with random vectors. And sort of the idea is similar to specializing calculus to working with matrices. We're going to be doing probability working with matrices and vectors. And so we have to customize some of the tools we have and extend them beyond the scalar case. All right, so let's get started. So a random vector, we're going to let z be a p-dimensional random vector. And a random vector is a vector such that each element of the vector is a random variable. Okay, so that's pretty straightforward. A random vector has elements which are random variables. And the expected value of a random vector is, well, we apply the expectation to each one of its elements. Okay, so that's pretty straightforward. And expectation is still linear. So we're not working with scalars anymore, but if we have random vectors, z and w, and scalars a and b, then the expectation of their linear combination, we can pull out the scalars and distribute across the sum, just as we could in the scalar case. Okay. And also, if A is a matrix here, so here A is scale, here A and B are scalars. A is a matrix, okay, and I'm just denoting it with the bold syntax. A is a matrix, then it still works linearly. So if you multiply a constant matrix times a random vector, expectation of A times Z, you can pull out the constant A. Okay? This actually, convincing yourself of this is a little more difficult. You can write it out and sort of see how things distribute, but easier to just sort of take it and we'll work with it. But if you do write it out, you can convince yourself pretty clearly. Okay, so continuing on, so we have expectations. What about variances? So the variance covariance matrix, okay, sometimes we'll call this just the covariance matrix, sometimes we'll call this just a variance matrix, but the variance covariance matrix of the random vector z is a p by p matrix. It's the following, okay? So here we have we denote it variance. So this is the variance covariance matrix, and it is the following. Along the diagonals, we have the variance of z1, z2, so on and so on, to zp, okay? The off-diagonal terms are covariances. So the covariance of z1 and z2 is the matrix element 1, 2. So this is row 1, column 2. The covariance between z1 and z2 is there. Okay. So what we're doing here is we're basically forming a matrix of pairwise covariances, right? So there's covariance z2, z1. This is row 2, column 1. So it's a covariance between z2 and z1. Right? So we're just basically combining all the covariance information in a matrix. And not only that, but I mentioned that diagonals are variances, right? Remember that the covariance of a random variable with itself is the variance, right? That was one of the facts we discussed in the miscellaneous facts lecture. So with that in mind, this is actually the covariance between z1 and z1, right? So actually, just this covariance matrix is just collecting all the covariances where element ij has the covariance of zi, zj. Okay. The correlation matrix, it shows up in one of your homeworks, so you may have seen it informally, but the correlation matrix is very similar to the variance matrix, except for instead of pairwise covariances, for the correlation matrix, we have pairwise correlations. Okay, so that is zi, or the ij entry in the matrix, and the correlation matrix will have a correlation between z1 and 2 instead of the covariance matrix. Okay? Or instead of the covariance between them. All right. And so yeah, so more detail about the correlation matrix here is instead of covariance here we have the correlation where recall that the correlation is the covariance divided by the standard deviations. All right. So that is the definition of a variance covariance matrix, which again we'll call variance, sometimes called variance matrix, sometimes called covariance matrix. If it's a matrix which in some way has variance in it, this is what we're talking about. So some facts about the variance covariance matrix. The first one is that a shortcut for computing it is the following. Okay, and that is expectation ZZ transpose minus expectation of Z transpose. Okay. This should actually look pretty familiar. For a scalar, we have the variance of x is the expectation of x squared minus the square of the expectation. Hope you've seen this before. We've referenced it in this course. This is actually the extension, this top line is the extension for random vectors, right? Where instead of squares, we take what's called the outer product. So the outer product, this is a column vector. The outer product is, you do a vector times its transpose. This is obviously different from the inner product, which the inner product is row times column. So this gives you a matrix when you multiply that. Okay, so this is a fact about variances. We have the shortcut. Also, this is similar to the scalar case again, but if you add a constant vector and a scalar b, what happens is when you take the variance of this, the matrix, the vector A doesn't matter in the sense that it does not affect the variance, and we can then pull out the b and square it from the variance. So this is just like the scalar case. Okay? So again here, this is a variance, i.e. a variance covariance matrix of this random vector, and we can ignore the constants, pull out the scalars, and square them. Okay, but what happens if instead of multiplying by a scalar, we multiply by another matrix? Right? We do that, we have to be careful here because again, matrix multiplication is not commutative. What we do is we put one out front, one out back with a transpose. Okay, so variance of C times the random vector Z. So C is a constant. We pull it out and we put it out back. Okay, and again, this generalizes the scalar case, right? So this is a generalization because if C is a scalar, then we pull it out to transpose. The transpose is itself. You can move around scalars in this matrix multiplication, and you get exactly what's above. All right. So, with some properties of random vectors, we have expectations and covariances. So, we're going to let mu be a vector, and sigma, this is a capital sigma, be a covariance matrix. Okay? I should mention one thing about covariance matrices before we move on too much. But the covariance matrix is symmetric. The reason it's symmetric is that the covariance between Z2 and Z1 is the covariance between Z1 and Z2, right? So if we were to flip the role of rows and columns by taking the transpose, we would have, it is symmetric because this element is equal to this element and so on and so forth. Okay. Okay, so we have a covariance matrix sigma, a vector mu, and so with those in hand, we can define a multivariate normal distribution. Okay, multivariate normal distribution, what we give it is a mean vector mu, a covariance matrix sigma. It's a distribution such that if we have a random vector distributed multivariate normal mean mu covariance matrix sigma, what it means is that the Zi, the ith element of the matrix, is distributed normal mean mu I variance sigma II, right? So the covariance, the variance is given by the ith element along the diagonal of the covariance matrix. And not only that, but then the covariance between Zi's and Zij's is given by the off diagonals. Okay, so a multivariate normal means that for each element in the random vector, we have a normal distribution mean ui variance given by the appropriate diagonal term, and then the covariance terms, that is how they relate to one another, is given by the off-diagonal terms. So an easy way to think of this is it's basically a way of tying together a bunch of univariate normal distributions. We have these univariate normal distributions, and then they have covariances given by the covariance matrix sigma. Okay? So we have some new properties. We have covariances. We have random vectors. So I want to find, here's an example, I want to find the expected value of ZZ transpose. Okay, so again, this is an outer product because this is a column vector times a row vector when I take the transpose here. And so if Z is multivariate standard normal, by standard normal, what do I mean? You can take a guess, but by what that means is that Z is normal means 0, where this is a vector, okay, and covariance matrix identity. So a multivariate standard normal is sort of the best case, mean 0, variance 1. Off diagonal terms are 0, so there is no covariance between them. Okay. If Z is multivariate standard normal, then the expected value of ZZ transpose is, here I just perform this outer product, right? So when I take this outer product, I find this element by this times this, and so on and so forth. I can move through. Okay. So this is the product of normals, right? And rearranging our variance identity, right? So remember our variance identity from previous slide. We know that the variance is equal to the expectation of the outer product minus the outer product of the expectations. We get that the expectation of ZZ transpose is equal to the variance plus the outer product of the expectations, right? So here what I'm doing is I'm putting this piece here over on this other side of the equation, right? Why is that important? Because, right, what we want to find is this expected value. Here we have this expected value is some covariance matrix plus the outer product of the expectations, right? But we know these terms. So if Z is multivariate standard normal, then the variance becomes, this is the variance covariance matrix. The expectation we know because, as we talked about, this means it's mean 0, variance identity matrix, right? So this is 0, the outer product of the 0 vector, which is 0. This is the variance of a multivariate standard normal, which is the identity. We just get the identity. Okay. Another example, just to illustrate these properties a little more. So if Z is a multivariate normal, so here I haven't said standard, so I'm going to specify that it has a certain mean vector mu and a certain variance covariance matrix sigma. So let A be a matrix. Now the question is, what's the distribution of matrix A times the random vector Z? So, well, what we have to know, so first we're going to compute its expectation, just to be clear. Its expectation is, well, remember the property of expectation, we can pull out the matrix A. Okay, apply the expectation to Z, we get A times mu. And the variance works the same way. So remember the variance, I'll jump back to the slide here, but in this slide here, what we had is the variance of a vector or a matrix times a random vector. What we do is we pull out front, pull out back, and take a transpose. So the variance, what we do is we pull out front, pull out back, and take a transpose times the variance of Z. We get this. Okay. So we have the expectation, we have the variance. That is not enough to determine its distribution in general. However, because we're working with normal distribution, we can recall the following fact from the appendix. So remember, this is the appendix we've been referencing in this class, the one that we posted on the course website from Applied Linear Regression. And the fact in the appendix, which we've been using, which we've used on the previous homework, is that any linear combination of normals is normal. Okay, so if you give me a linear combination of normal random variables, it is again normal. Okay, so what we have here is each one of the so this is A times Z. This is going to give me a random vector, which is each one of its elements is a linear combination of normals, because each of the z's is normal. Okay, so because each one of the elements is normal, this is in fact a multivariate normal distribution with a different mean and different variance. Okay, so what this means is that this distribution is actually normal, multivariate normal, mean A mu, variance A sigma A transpose. Okay, and we sort of have three pieces here. The first one is it has a certain mean. The second one, it has a certain variance. The last one is linear combination of normals is normal. So when we take this this matrix product here, we get back a normal distribution. Okay. So the last one I'm going to do here, so this is the same problem, different direction. We're going to go backwards. This one's a little more challenging, so I just want to sort of introduce it as something to think about, not necessarily something that you need to know in terms of, we're going to introduce a new linear algebra technique here. But so what we want to do, I'm going to assume that we can generate observations from a standard multivariate normal. Okay? So we have a standard normal multivariate, so it's vector 0 here. Covariance matrix is the identity matrix. And the question is, how can we generate observations from a normal mean mu covariance matrix sigma if we know mu, we know sigma, and we can generate these? Right? So what we want to do is basically take some multivariate normal and use it to generate an arbitrary multivariate normal for mean mu and covariance matrix sigma, which are specified. Okay. So facts we need for this, any covariance matrix is positive semi-definite. Okay, remember what this means. We talked about this in the first part of this lecture. This means that the eigenvectors, they're not positive, they are non-negative. And the reason that they are non-negative instead of positive is that I've said semi-definite. These are non-negative eigenvalues. For any positive semi-definite matrix, it has what's called a Cholesky decomposition. Okay, a Cholesky decomposition is where we can write A is L transpose. Okay, for some matrix L. Okay. The additional fact that Cholesky decomposition is unique when A is positive definite, but we're actually not going to need this. So there's just a couple of facts here. So with these facts in hand, you can think about this. I'll give you the answer on the next slide, but take a moment. Can you use this fact that we have basically a covariance matrix, which can be decomposed into something that looks like LL transpose? Can you use that to define from these standard multivariate normal z's a random variable which has distribution given here? Okay, and just as a hint, obviously, because I introduced this, you're going to have to use this Cholesky decomposition in one of these matrices L, right, which exists because covariance matrix is positive semi-definite. So take a shot. You can pause the video. I'm going to go ahead and move on into the solution. So if Z is multivariate standard normal, right, then what we're going to do is take this transformation. This should look sort of familiar. What we're taking is a mean 0, adding a mean, right, so the mean is going to be mu, and then performing a transformation, right, where we're multiplying, basically we're performing This is similar to the univariate, or the scalar setting, where you do a sigma z plus mu. And this is sort of the inverse operation of the x minus mu over sigma standardization, right? So this takes us to standardized, this takes us to be unstandardized. So mean mu variance sigma squared. So this looks like this, but with the matrix setting, right? So here we've multiplied by L, the matrix L, and a standard multivariate normal C. Okay, so what's its mean? What's its covariance? Right, I claim this is right. Well, its mean is, we can go ahead and just apply the expectation, right? Sorry. So this is constant, and z is mean 0, so this becomes expectation of mu, which is just mu. Okay, and then for the variance of LZ plus mu. So here we're adding a constant, right? Remember, adding a constant to a variance covariance doesn't affect it. So we get variance of LZ here, and then we're multiplying times a vector here. So what we're going to do is L variance of Z times L transpose. Okay. And remember, variance of Z is what? Well, it is standard multivariate normal, so this is the identity. So we have L times the identity times L, which is equal to the transpose, which is equal to L transpose, which is equal to, based on this Cholesky decomposition, equal to capital sigma. Okay, so this is an example. Am I going to drill you on the Cholesky decomposition? No, but what's important about this example is it just illustrates properties of transformations of random vectors, right? What happens to their mean, what happens to their covariance matrices. The last bit, I guess, which I haven't mentioned, but I should, is that right, we've said what this thing's mean is, what its covariance matrix is. Again, it is multivariate normal for the same reason as we've discussed previously, which is that each one of the elements in this random vector is a linear combination of normals, and therefore normal. Okay, so that's all I have for this lecture, and I look forward to seeing everybody next time.